Morning. Hi, everyone. Welcome to our session today. We'll be talking about Checkpointless and elastic training on Amazon SageMaker HyperPod. I am Anirudh Vishwanathan. I'm a senior product manager with the Amazon SageMaker HyperPod team. I work primarily on distributed training at scale and framework-level optimization. I'm here with my colleague, Arun.
Hi, everyone. My name is Arun Nagarajan. I'm a principal engineer with the Amazon SageMaker AI team. I provide technical leadership for many of our products in SageMaker, including HyperPod.
Thanks, Arun. And we have a special guest. We also have Antonio from Salesforce.
Hey, everyone. I'm Antonio. I'm a researcher on our Salesforce AI research team. Been using HyperPod for almost 2 years, and happy to tell you about some of our experiences and some of the cool things we've been working on with HyperPod.
Awesome. Thank you. So let's dive straight in. So today, here's the agenda for our talk. We'll cover an overview of what Amazon SageMaker HyperPod does. We'll set the background on what it takes to train models at scale, and then walk through 2 new features, elastic training and checkpointless training, followed by a session from Tony, and close with a few takeaways. So let's start off with what HyperPod does. Amazon SageMaker HyperPod offers you essentially purpose-built infrastructure for foundational model training and deployment. With HyperPod, essentially, we've taken away all of the heavy lifting associated with manual cluster creation and managing your own self-managed environment, and have sort of built training and deployment stacks up from the ground, essentially providing you a way to improve your efficiency of model training, which in turn reduces the amount of time it takes for you to train and also lowers costs. So the benefits of HyperPod is that it offers you an extremely resilient training environment. The idea is that when you're training on HyperPod, you're typically training on multiple AI accelerators or GPU devices. And the idea with HyperPod is that it proactively screens every node or every device that's part of this training cluster for health checks, and make sure that the environment is set up correctly to give you the best training performance. All of this is done automatically for you, and the environment is managed by Amazon. It also offers an extremely scalable environment for model training, where essentially you can run training workloads on single spline topology, where essentially all of these devices are on the same rack and have the same physical wiring, so it gives you the best training throughput and performance. It supports a variety of instance types, spanning the newest accelerators for both GPU-based and Trainium-based instances. And essentially, HyperPod offers this managed service, which is fully observable, lets you highly customize your environment, and has a variety of DL armies that can run on HyperPod as well. So here's an overview of what HyperPod offers. It offers essentially a choice of both Amazon EKS or Slurm for orchestration. It's compatible with a variety of frameworks from PyTorch, TensorFlow, Nemo, and so on. And under the hood, it runs either with the NVIDIA Nickel libraries, which is the collective communication library, or with the Neuron runtime for Trainium-based instances. And it also supports both GPU and Trainium-based accelerators. And of course, you can connect a variety of storage where your data might reside for model training. So with this background, let's now transition into the crux of the talk. So let's step back and think about some of the fundamental challenges with large-scale model training. I'd like to leave this up on the screen for a moment. And the graph here is data from an organization called Epoch AI. And they've tracked usage patterns in terms of cluster sizes used for model training over the past decade. We've seen the size of these clusters grow from hundreds of accelerators to thousands to now hundreds of thousands of accelerators, which is nearly a 20 times increase over the past 10 years. And so cluster sizes are essentially becoming larger as models become more sophisticated. And the challenge is that as you have larger clusters, the likelihood of failure also goes up. So what we've got here, and let me walk you through this chart, is that every column represents a different cluster size. So a cluster with 4 nodes essentially has 32 GPUs, and we go all the way up to 1,000 plus nodes, which is upwards of 8,000 GPUs. And every row out here represents the probability of a node in that cluster failing during a specific hour. And so the way we read this chart is that essentially as cluster sizes grow larger, the likelihood of a failure actually increases, which means that if you're on a cluster with 1,000 nodes and you have a probability of failure at 0.02%, that cluster is going to likely experience a fault every 4 or 5 hours. So let's just think about this practically, right? Which means that over the duration of a single day's worth of training, this cluster is going to be experiencing 4 or 5 faults, each of which can probably take upwards of an hour for recovery operations. Think about this. That's essentially 1,000 nodes, 8,000 GPUs, sitting completely idle during recovery operations, just waiting for recovery and resuming from your checkpoint. That's essentially a significant challenge. So here's what happens when model training actually kicks off. So typically with model training, you have a sequence of steps where at every step, there's some amount of data that the model sees, does a weights update, and then goes on to the next step. There are periodically model snapshots or checkpoints that get saved, and checkpoints are typically done at a cadence or predefined frequency. And anytime there's a failure, so in this case, there's a failure that happens after step number 4, you need to essentially roll back to your last save checkpoint, redo steps 3 and 4 because they happened after the last save checkpoint, and then resume training. And so during this entire process of checkpoint-based recovery, you need to roll back training, redo a bunch of steps, and then resume training, which means that you're essentially paying a cost where your cluster is sitting idle, and you're redoing work that was already previously done. So that's one challenge where as cluster sizes grow, the probability of failure tends to increase, and recovery from failure also starts to become more complex. Additionally, there are other challenges with clusters that become larger. So the larger the cluster, the more likely is this cluster going to be used by multiple teams within the same organization. And so you can think of this cluster running a bunch of fine-tuning jobs, short-lived experiments, inference workloads, long-lived pre-training runs, and so on. And even if you look at specific inference workload patterns, those are typically diurnal, right? So you have essentially a peak during the day and then a drop-off at night, which means that your cluster utilization is sort of going to vary over time, and there are going to be these pockets of opportunity at night and during weekends where the cluster is completely underutilized. Again, this means millions of dollars potentially sitting idle, where other workloads could have opportunistically used this capacity. So with that background, let's talk about the first feature that we've launched. It's called Elastic Training on Amazon SageMaker HyperPod. So the fundamental challenge that we're solving with Elastic Training is this problem of infrastructure underutilization. And going back to that previous graph where we saw diurnal cluster utilization patterns, we wanted to think about ways to optimize cluster utilization. And the fundamental challenge that we have today is that training workloads are fixed in the sense that once you kick off a training job, you have the same number of nodes and the same number of accelerators that participate in this job from start to finish. And what this means is that anytime there are more resources available, these might be nodes that free up from other jobs that had finished, you need to essentially stop this training job, reconfigure a bunch of hyperparameters, and then resume training to use the additional set of resources. On the flip side, let's say there's a higher priority workload that needs nodes occupied by this current training job. The only way to sort of give back nodes is to halt this training job completely and return resources. So it's this all-or-nothing choice that customers face where you have to either over-provision the cluster to ensure training continuity or essentially stop the job entirely to give back resources. And so this entire overhead of workload management can mean customers spend hours sort of observing resources in their cluster, manually defining hooks to dynamically scale up or scale down their training workloads. So with elastic scaling on Amazon SageMaker HyperPod, we've enabled your training workloads to dynamically scale up and down in response to available cluster capacity. And what this means is that Training jobs on HyperPod can now automatically scale up when free resources become available and scale back down when those resources are requested by higher priority workloads. All of this happens under the hood. You simply configure your training job, kick it off, and then anytime new resources become available, the job scales up and it scales back down when those resources get consumed. In turn, this simplifies your operations because you no longer need to manually babysit the cluster, observe free nodes, and reconfigure these training parameters manually. This is taken care of completely under the hood, and it also preserves training convergence by ensuring that the global batch size, or the amount of data that is seen at every step, remains constant across the duration of the training job. With this, customers can easily get started either through the HyperPod recipes, or you can make custom modifications for your own scripts to accelerate your training workflow. So here's what it looks like in an animation. So let's say you start off a job with 4 nodes. That job now can scale up to 8 nodes because 4 additional nodes became available. It's running at 8 nodes, 4 more nodes become available, so we've gone from 4 to 8 to 12. At 12 nodes, what happens is there might be a higher priority workload that needs a couple of nodes. And so instead of halting completely, this job is able to scale back down from 12 nodes to 8 nodes and continue to run in the cluster. Once resources open up, it scales back up to 12 nodes and concludes. What's notable to observe here is that despite the number of nodes participating in this workload fluctuating over time, the loss function continues to decrease, which is most important for training continuity. With that background, let's dive under the hood, and I invite Arun to walk us through some of these details in terms of how elastic training works. Arun, over to you.
Thanks, Anirudh. Now, let's dive into the technical architecture behind elastic training. We have modified the HyperPod training operator to support elastic training mode. The operator works through 4 key features, and we will talk through them. The first is the continuous cluster monitoring, where whenever you have new resources available in your cluster, for example, you scaled up your cluster or a currently running training job completed, new resources are available, and this cluster sends a scale-up notification for your jobs. The second is the graceful preemption. Whenever you have a lower priority job, currently the only option for you to give up resources is to fully terminate the job. You cannot give partial resources. Even if the higher priority job did not need all of the resources occupied by the lower priority job, we simply have to terminate the lower priority job. With our system, we are offering an ability so that you can continue to run the lower priority job with reduced resources. Sure, the lower priority job will run with lower throughput, but your cluster utilization is going to be high. This is a game changer because of 2 things. One is that previously the lower priority job, which would have been kicked out, is currently running and making progress. And the second thing is that your cluster utilization previously would have been lower because nobody was going to use that compute. Now it's going to be used for the lower priority job to make progress. The third part is the automatic training stack reconfiguration. And you may know that whenever you have to scale your training job from smaller count to a larger count or vice versa, you have to adjust the training parameters which are critical to maintaining the training quality and convergence. And you typically have to manually adjust these parameters and restart your job whenever you change your world size. Our system offers you an ability to specify scaling policies so that you can tell SageMaker, here is the set of parameters which we need to apply for various world sizes. And you don't have to manually be involved in this process. The training operator automatically applies these training parameters at the right point whenever the scaling activities happen. And the fourth one is the automated workload management, where the training operator works with the HyperPod task governance system so that your cluster utilization is maintained high. Your administrator can continue to set the policies on limits and quota on the workloads and teams and projects involved in your cluster, and the Elastic training still respects those policies so that your cluster utilization can be maintained high. The key thing to note here is that all of this is happening automatically. Your data scientists can focus on model building and not have to worry about infrastructure stuff. Now, building on that understanding, let's walk through how the system works end-to-end during one of these scaling activities. As we talked about, the system continuously monitors changes in resources, including addition or removal of resources. Once the system observes a change, it kicks off a scaling process. And this system will send a synchronized coordination signal to all the training processes, telling that a scaling event is imminent. Now the training processes, they know that they need to take a checkpoint so that at a later point of time, you can resume. The checkpoint typically consists of the optimizer state and model weights, and presumably your training code already has code for taking the checkpoints in the traditional sense. Now that the operator has told all the training processes that, hey, you need to go take a checkpoint, now the training operator will terminate all the training processes and restarts them with the new configuration. That would be either with more number of training processes if it's a scale-up event, or a lesser number of training processes if it's a scale-down event. And when these training processes bootstrap, they realize that they have been restarted, they will load the checkpoint, understand that they need to reconfigure and redistribute the checkpoint, and they will continue training. All of this happens automatically for you, and it takes a few seconds for this to complete so that your training job can continue and your GPUs don't have to sit idle. All right, now to the fun part. How do you get started? We have made this incredibly simple for you to get started. If you're using standard architectures like Llama, Qwen, DeepSeek, you can get started with zero code change. That's right, there is no code change needed. All you have to do is bring in your data and set up the minimum node count and maximum node count, and that's it. You can kick off the training on HyperPod with the kubectl command or with the HyperPod CLI, and you're good to go. The HyperPod recipes do all the heavy lifting needed, including setting the right parameters to invoke the HyperPod training operator to be running in an elastic mode, and also supplying the elastic scaling policies needed for various node counts so that the learning rate and batch size parameters are optimized for various node counts. Now, if you have advanced setup and you have custom training scripts, then we have a path for adoption as well. This is slightly more involved, where you have to make some changes to the job specification, and you need to supply the elastic scaling policy where you have to say the minimum replicas needed, maximum replicas needed, and the scaling unit, which is what we call the incremental step count. Then you need to make some changes to the training script itself, where you have to import the elastic event handler from our elastic agent, and you have to handle the events sent by our operator. Remember how we talked about the operator being responsible for notifying all the training processes that a scaling event is imminent, and this is the code behind that. You can see that you can register for those notifications, and you can invoke your existing checkpoint load and save primitives, and that's all you need to do. I want to highlight that even with the custom adoption path, the heavy lifting is done still by the operator on detecting the resource changes, notifying all the training processes, terminating them and restarting them with the new configuration, and applying various scaling policies. All of that is handled for you automatically. You just need to implement certain hooks so that the operator and your training code can work together. Here is a visualization of the elastic scaling job in action. You can see that we had varied the world size from 1 to 2 to 8, and you can see the tokens per second closely following, the throughput is closely following the world size available for the training. You can also observe that the loss continues to decrease and the training job was not interrupted in this process. To wrap up, elastic training marks a fundamental shift in the way you think about AI infrastructure. Long gone are the days where you have to manually allocate certain resources for certain jobs, and then you have to play Tetris to make sure that every job fits in your system. We now have a system where you can configure it to dynamically adjust to the cluster reality, and we also offer you a mechanism so that you can continue your training without sacrificing your training quality and convergence. Whether you use the recipes or you go with the custom path, the path to adoption is pretty straightforward. We encourage you to start with a pilot project and see the gains for yourself. With that, I will hand it over to Anirudh, who's going to talk about our next part, which is the Checkpointless training on HyperPod.
Thank you, Arun. All right, so this is the next shiny feature that we have for you today. Checkpointless training on HyperPod was announced yesterday during Swami's keynote. In this section, we'll sort of dive deeper into how it works under the hood. So going back to sort of set the context here, right? The fundamental challenge is that with large clusters, and even smaller clusters for that matter, checkpoint-based recovery leads to idle time during training. So anytime there is a fault, essentially you need to halt the cluster, reload your last saved checkpoint, and then resume training. But the challenge is that even recovering from the last saved checkpoint isn't as trivial as it sounds. And this is primarily because with checkpoint-based recovery, there's a sequence of events where every event needs to happen first before the next event can happen. So it's this cascade of events that are blocking and sequential. So the idea is that the moment there's a failure needs to be detected, then you need to reinitialize communication and set up the topology of all of the nodes that participate in training, go back, identify your last saved checkpoint, reload that, reload data loaders, and a whole sequence of events happen before you have that first training step that happens post-recovery. So the challenge essentially here is that the sequence and sequential sets of steps which are blocking means the cluster is idle. And with hundreds of nodes or thousands of nodes, that's millions of dollars in wasted compute during recovery operations. So with checkpointless training, we've enabled cluster recovery to drop from hours on self-managed clusters to under a few minutes on HyperPod. And in turn, accelerating recovery times essentially means that you come to market faster, because if you're training models over a long duration, there can be days often spent in recovery operations over a long-running training workload, which now can be done in basically a few minutes. That's the fundamental shift in checkpointless training and what it enables. The idea with checkpointless training is that once you've configured and set it up, failure recovery is fully automated, and there's no longer sort of any manual overhead that you need to take care of when recovering from training. The idea is that you are able to maintain continuous training progress without having to roll back to your last saved checkpoint. In turn, that means essentially no more lost progress or no more wasted compute, because you essentially pick up from the current epoch that you were running, even in the event of a fault, without having to roll back a few steps to the last saved checkpoint. And so this capability essentially enables you to scale with ease across tens to hundreds or thousands of accelerators, and we have pre-created recipes that you can use for your own training workloads, as well as offer a suite of components that you can pick and choose and integrate with your own custom PyTorch-based scripts. So here's an overview of what checkpoint-based recovery looks like and versus what checkpointless training really does. So on the left, we have a cluster which is showcasing traditional checkpoint-based recovery, and the one on the right is essentially checkpointless training. So we start off where essentially the cluster might experience a fault. So let's just let this loop in one sequence. So if you look at node 7 is going to experience a fault. So it turns color, and essentially that's a fault that occurs. With checkpoint-based recovery, you need to sequentially reinitialize each of those nodes, which means that it can take several minutes for that initialization process to happen. You need to then reload your last safe checkpoint. Once that's done, you rehydrate your data loaders. So you essentially pre-process all of the data batches that need to get fed to the model and then resume training. This entire sequence of recovery operation can mean tens of minutes to potentially an hour on large clusters, versus with checkpointless training, you're able to recover in a couple of minutes or so. So here's what performance actually looks like. The latest generation of Amazon Nova models were trained using this capability on thousands of AI accelerators. Internally, we've tested with cluster sizes with upwards of 2,000 GPUs. And traditional recovery, which is checkpoint-based, can be anywhere between 15 to 30 minutes. But with checkpointless training, we're able to recover in under 2 minutes. And this is essentially an 80% improvement in fault recovery capabilities. We have similar results that hold true even at smaller cluster sizes. So even with clusters with 16 GPUs or 256 GPUs, we see that traditional recovery might take about 5 minutes or so. But with checkpointless training, it's an order of magnitude faster, and recovery happens in under a minute. And what this enables essentially is that even with clusters with thousands of accelerators, good put is upwards of 95%. So you're basically maximizing utilization of your training infrastructure with this capability. So to put this in perspective, right, if we look at this cluster of 2,300 GPUs, if you have a training run that's spanning a couple of months, traditional checkpoint-based recovery overhead over the duration of that training run of 2 months can mean multiple days are spent cumulatively just in recovery operation. Whereas with checkpointless training, that now drops to a few minutes, saving you millions in essentially training costs over the duration of this training run. So with that overview and of performance, I invite Arun back to walk us through how checkpointless training works under the hood. Arun, over to you.
Thanks, Anirudh. Checkpointless training is built on 4 key innovations that work together to eliminate bottlenecks in the traditional distributed training systems. Let's walk through one by one. The first one is the optimized collective communication initialization. Typically, in a distributed system for training, you have many processes running across many nodes, and they need to talk to each other to exchange data during training. For example, in a distributed data parallel training, the ranks need to all reduce the gradients after finishing the back propagation operation. However, before the ranks can talk to each other, they need to establish communication with each other. And typically, this is done through a centralized coordinating system, which is going to be a bottleneck when we are talking about the thousands and thousands of processes which we demonstrated in our previous slide. This can add up to minutes because of this bottleneck in the centralized initialization system. With our system, we eliminated this bottleneck by moving away from the centralized coordinating system towards a peer-to-peer connection establishment through HyperPod signals. This helped us save minutes, and we were able to do this in seconds. The second innovation is about memory mapped data loading. As you know, the training processes need access to the data whenever they need to start training. However, the data needs to go through some sort of pre-processing before the actual training can begin. And depending on how complicated your pre-processing pipeline is, this step takes up to minutes as well. You may be wondering, what's a big deal about spending a few minutes before the training start to finish the pre-processing? That intuition is right. However, when you have failures, you still have to pay the cost repeatedly. So every time a failure happens, you need to pay the cost of pre-processing your data, feeding it into training pipeline. And during this time, this is a synchronous operation. All of the compute, expensive compute, is sitting idle. We solved this by introducing a cache so that the pre-processed data is saved in the cache using a shared memory and memory mapped data files, so that when the training processes resume, they do not have to wait for reprocessing of the data which they are expected to wait on. In this new world, they can instantly get started because the pre-processed data is already readily available for them. The third innovation is the in-process recovery. In traditional distributed systems, as we talked about, there are many processes and many nodes which are collectively running together. And the current failure recovery mechanisms, what they do is that you are required to terminate the whole job and restart it, meaning all the processes are terminated and all their state is lost, and the new processes are kicked off, and then they need to rehydrate their state. With our system, we are replacing the failed processes with hot spare processes, and we do not touch the healthy processes. We leave them alone with their states. These spare processes join the training, and they continue to train with minimal interruption. The fourth and most innovative component is the checkpointless recovery itself. Traditionally, you will have to take checkpoints. The training processes need to take checkpoint at certain intervals, and when a failure happens, the processes need to roll back, repeat some of the steps, and continue. With our system, building on top of the in-process recovery, what we have achieved is that the newly joined training processes do not need to load from the checkpoint, but rather they hydrate their memory from the other healthy processes directly using the high-speed network. This way, the training interruption time is reduced dramatically, and that's how we achieve the sub-minute recoveries that Anirudh shared, and also the 95% good put, even at the large scale. All right, that sounds exciting. So how do you get started? Just like the elastic training, we have made this quite simple for you to get started. And we have two approaches. First is, of course, the HyperPod recipes, where you can get started if you are using standard architectures by using the recipes, downloading it, and then using the kubectl command to run it on HyperPod. The recipes do the heavy lifting for you, including setting up the operator to run in this checkpointless mode, setting up the collective communication optimization, and then the memory map data loader, in-process recovery. All of that setup is handled for you, and you can just kick it off. We think this is the fastest path for adoption for most teams. But if you have special requirements and custom training code, we have an incremental adoption path for you. We have componentized each of these so that you can incrementally adopt each component, observe the benefits, and continue to adopt all of the features together. The first one is the optimized collective communication initialization, and it's the easiest to adopt. You just need to set a couple of environment variables to your training jobs. The first one is instructing it to not use the centralized initialization system. The second one is telling that it needs to use the HyperPod-based optimized initialization. And that's it. You already saved a few minutes of recovery time every time a fault happens. The second one is the memory mapped data loader. We talked about how we have a cache where you can store the pre-processed training data so that during fault recovery, you do not need to spend all the time reprocessing those data. This one is also pretty easy to adopt. We have provided a library with a wrapper, which is quite non-intrusive, and all you have to do is to point to a cache location for storing the memory mapped files. Moving on to the in-process recovery and checkpointless recovery components, this one is a little more involved. You have to do a couple of changes, including changing the strategy used by your PyTorch training code to point to the HyperPod specified checkpointless strategy. This instructs the framework to not use the classic checkpointing, but rather use the restartless checkpoint that we have implemented. Secondly, you do have to wrap your training loop with the HyperPod wrapper annotation that we have provided, which takes care of the heavy lifting for health checks and having the coordination with the HyperPod PyTorch operator. You can imagine that all the complicated handshake which are needed to rehydrate the state from healthy peers, all of that is taken care of for you by these two changes. I want to conclude by saying that we took a deep look at the existing framework level limitations that are present in the traditional distributed training systems. And we have eliminated a lot of bottlenecks from these systems so that you as our customers get the most value out of the compute instances that HyperPod offers. I hope that we have convinced you to give it a try on all these new features, and I'm excited what you are going to build with them. With that, I am thrilled to invite Tony, who is going to talk to us about how Salesforce is using HyperPod. Tony.
Thank you. Hey everyone, so I'm Tony with Salesforce AI Research, and we've been HyperPod customers for over 2 years now, and I wanted to take a little moment to just share with you what our use case looks like. So we have very heterogeneous workloads. Of course, standard LLM training, but we also have things involving multimodality, which is a lot of like speech and image processing that also happens on the cluster. We do a lot of fine-tuning in RL, so these are high-volume jobs that are often much shorter than long-running LLM training, and can be kind of bespoke and custom. And we've got batch inference jobs, which can run at varying sizes over varying time periods. And checkpointless and elastic training helps us manage this heterogeneity in an easy way. So I'm going to dive a little bit deeper into what exactly we do for batch inference. So I like to use SGLang. It's an open serving framework, happens to be my favorite. And the way we set this up is we have a job script which can run on kind of a head or a login node style architecture. It's really lightweight. All it does is load balance to one of your end worker nodes, and each worker node is a very simple, straightforward SGLang server. Of course, all of the workers are connected by disk substrate, distributed file system, or S3, anything of that nature. And I'm going to dive a little bit deeper into one particular use case within the umbrella of batch inference, because we have several. And I will motivate this use case as follows. So I want to pause and draw a little bit of contrast between kind of when we think of AI or even just learned software and how that is a little different than how we've come to traditionally consider human programmed software. And one key contrast is this idea of non-determinism. And you can think about this at each layer of the stack. So you can think about the app layer, where traditionally, if software was working correctly, it would give you the same answer every time. And now we have a lot of AI systems where even in the app layer, there are key icons like regenerate, and regenerating responses and trying different prompts and tweaking is actually a core part of the application experience. Even at the algorithmic layer, though, outside of the application, you have things where the neural networks themselves are sampled in a stochastic manner, and that's actually, at the algorithmic level, the entire way that it's supposed to run. Again, in contrast with how most applications have been built on deterministic algorithms. And even going one layer lower into the stack, standard CPUs are highly deterministic pieces of software, whereas when you're running on AI accelerators, it's actually it's in the spec that you can get non-determinism when running due to non-commutative properties of the floating point arithmetic on these accelerators. And so all of this is to say is that there's a very deep way in which non-determinism and stochastic behavior is embedded in the AI stack. And from our perspective at Salesforce, we think about what is the business impact of this? Because we have customers across a variety of industries. Healthcare and financial services are two industries in particular that are very much concerned with this concept of non-determinism, right? So they care a lot about having deterministic and auditable outputs. And for them, having a way to grapple with this non-determinism is important. And they kind of are still figuring out how to handle this. And they're really trying to navigate this. And one thing that could be of interest to them is how could you build AI systems that help bridge this at kind of various levels of the stack. So as I mentioned, it was a multi-layer problem. That was kind of setting the broader picture. Let's now kind of zoom in and take a look at what actually happens with an AI model. How does this manifest? So in sampling of a language model, there's this parameter where you may have seen, depending on if you've used things like an open source or an OpenAI API, where there's a temperature flag. And this temperature flag can be set to various values, zeros, deterministic in theory. Again, of course, there's hardware non-determinism. But you can set this higher, and that makes the answers more or less random. And so what can happen is that when you have reasoning models and you set too low of a temperature, the reasoning model will degenerate, and it will basically produce completions that are repetitive nonsense. And the reasoning models, for example, many providers no longer even expose the temperature flag on those APIs because they don't want you to basically run into this edge case. So they basically set a higher temperature and they don't let you lower it. And so you may also recall the frequency and the repetition flags, which were two kind of tools in the API that helped you more easily control this and kind of mitigate against this. And as we've seen, it doesn't fully always work. So to motivate why we're studying this problem, you can actually see this screenshot. This is an actual screenshot from a leading software agentic coding tool. You've probably used it if you've written code or tested it. And as you can see, there is very clearly degenerate repetition. So while this is infrequent, it does happen in the wild. And the main penalties to address this fail in all cases, or they don't succeed in all cases, I should say. And so one work we did that heavily relied on batch inference on HyperPod was this LZ penalty development that we worked out this year. So why are we working on a new penalty? As I mentioned, there's already industry standard penalties that you can find in standard inference APIs, the repetition penalty and the frequency penalty, but neither of them fully solves the problem. So what is the repetition penalty? You can think of it as a binary approach, which basically says, if the token already appears in the generation, I'm going to downsample and make it less likely for that token to appear again. This basically entirely ignores token frequency. It's a very kind of crude metric. And so it's also lacking in memory. It penalizes all tokens equally, regardless of recency. So it doesn't actually work and experiences up to 4% degenerate repetition rates. For the frequency penalty, which is the other industry standard, we can also see that empirically it doesn't fully work. It tries to be more sophisticated than the repetition penalty by actually scaling the number of appearances and scaling the penalty based on this. But the problem is that it doesn't actually account or normalize for the length of the sequence, which can result in a situation where for very long completions, which is what you get when you turn on reasoning, because the models can basically think, and for thousands of tokens, let's say, you get very long sequences, that also makes the frequency penalty start to fail catastrophically when common tokens eventually get banned. So basically it's like saying you have a certain number of commas you're allowed to use in your response. Once you exceed that number of commas, you can't use anymore, and what results is the model wants to use a comma, but it can't, so then it makes up another token in its place, and it starts to degrade the response until it just becomes degenerate nonsense. So I'm going to tell you about the LZ penalty, which you can think of it as a variant of the two previous penalties, but it's different on a fundamental level. It's based on information theoretic principles that enabled you to more rigorously address this problem. So you may have heard of LZ77, but I'm certain you've used it because you've zipped a file on your computer. So if you've done that, that's LZ77. It's a data compression algorithm that has this property of being universal, which means it can basically work for any data type. We won't go too much into the details of it, but essentially what it does is it lets you look at the historical parts of the file, and then looking forward to the next chunk of the file, it allows you to pattern match the next chunk compared to, let's say, a lookup table or a sliding window of previous chunks. And that pattern match is what enables the compression. So as I mentioned, n-gram repetitions, and it's based on pattern matching, not just naive frequency counts. So how do we actually apply this LZ algorithm to the language model? During the sampling of a language model, it looks like this, where we have a context. That context gets fed into the language model, which produces what's called logits. These logits is what tells the sampler what probability to assign to every possible next token. With the LZ penalty, we, in parallel from the language model, are running the data compression algorithm. So you can basically think of it as running gzip or something very similar to gzip right there in parallel with the language model. And then we're taking the output of that data compressor, and then we're fusing that output with the logits that come out of the language model. And then we're using this fused representation for the sampler. And what this enables is that the outcomes that the data compression algorithm thinks are very repetitive become very much down-weighted in the generations from the model. Because this data compression algorithm is actually the perfect thing to, in some sense, detect this kind of degeneration and repetition and redundancy. So empirically, we can see here, so the charts on the left are showing average score across temperatures. And so the temperature, again, is this parameter that controls how random the sampler is. Temperature 0 being the value most there to your left, is going to be greedy decoding that's perfectly deterministic. And so as we can swipe or scan the temperatures, we can see that the LZ penalty there, the LZ penalty there in red, is consistently within error bars of the best with no penalty and the best with the various two other penalties, frequency and repetition. Again, those are our baseline penalties. And without degrading accuracy, which is very important, you don't want to degrade your accuracy. This is, by the way, reasoning model, a Quen 32 billion parameter reasoning model, open source. We can see that the degenerate repetitions are uniformly, essentially virtually eliminated with the LZ penalty, uniformly across the board at any temperature, below 0.1% empirical discovery of any kind of degenerate repetition, whereas all the other penalties are maybe generously, let's say, somewhere between 1 to 4%, which is, again, pretty infrequent, but it also depends on your perspective, because getting a situation where you actually do see repetition or degenerate repetition is very bad. And so this also, again, goes back to why many of the model APIs don't let you use reasoning models at temperature 0 to let you kind of not have to deal with this problem of running into these degenerate repetitions. So here is a little bit more of an in-depth result. So these heat maps show every value of the repetition penalty in terms of its strength. So again, if you can tune both the temperature and then you can tune the strength of the penalty, and the stronger the penalty, the more it impacts the ultimate sampling from the model. The very top row of every heat map is the row that is the LZ penalty. So that's kind of like our row at just the one strength that you need. You don't need to tune it. And again, you don't need to tune it because of the universal property of the data compression algorithm. It works for any data distribution. But the other ones you do need to tune, and you can see that on the repetition penalty heat maps, you very often at low temperatures, and occasionally sometimes even at higher temperatures, do run into these kind of catastrophic failures with degenerate repetitions. Bringing things back to inference, you might be asking, okay, well, you're doing all this extra work with the LZ penalty. How does it impact your inference performance? And the answer is that the amount of work you do with the LZ penalty compared to the language model is very small. One, it parallelizes very neatly on the GPU. And two, as I mentioned, very, very small. At even just a 1.5 billion parameter model, the throughput slowdown is less than right about 0.5%. Latency is nearly on par. And then as you go up to even 32B, it goes down from 0.5% to 0.03%, essentially vanishing as the model even reaches medium size, the kind of inference impact of having to do this extra work for the LZ penalty. So one thing that we did was this is one line of research we worked on in parallel with dozens of other jobs all running on the same HyperPod. The final set of experiments that we presented, a subset of them here, you can reference our technical report for the full set of experiments. That was validated over about a week with other jobs scaling up and down. We went through over 25 billion tokens and over a zettaflop of compute. And yeah, so again, being able to run this and having elastic and checkpointless scaling up and down is very synergistic with how we want to scale up and down our batch inference and all of other job workloads. So with that, I'll have Anirudh come back and wrap us up.
Thanks, Tony. So folks, to summarize, we covered a couple of key launches in this session. So with elastic training, it fundamentally changes the way training jobs run on HyperPod. And so we can dynamically scale them up or down to take advantage of idle capacity in the cluster. This ensures training continuity and better cluster utilization. You can think of elastic training as sort of playing Tetris with your cluster capacity, growing and shrinking jobs as more capacity becomes available. And the second key launch is checkpointless training. This is a paradigm shift in terms of training resilience. And instead of going through a checkpoint-based recovery, which can take up to an hour, checkpointless training can offer you recovery times that are in minutes. This has good put numbers upwards of 95% on clusters with thousands of nodes. And with that, we wrap up our talk. Here are some resources. We're excited to see what you build with this. We'll be available off stage for any questions that you might have. Please do leave feedback on the session within the app. Thank you so much.